Good afternoon, everyone. Today, the Atom Seminar has the great pleasure to welcome Professor Randall Snurr. Professor Snurr holds a bachelor's from the University of Pennsylvania and a PhD degree in chemical engineering from the University of California, Berkeley. Currently, he works as a professor at the Northwestern University and is the director of the Chemical and Biological Engineering Department. His research focuses on adsorption, diffusion, catalysis in nanoporous materials. He is interested in novel materials such as metal-organic frameworks and also in traditional materials such as zeolites that are already widely used in the industry. This leads to application of nanoporous materials in adsorption separations, catalysis, membrane processes, sensing, and energy storage. His honors include a career award from the National Science Foundation and the 2011 Institute Award of Excellence in Industrial Gases Technology from the American Institute of Chemical Engineers. He was also elected a corresponding member of the Saxon Academy of Sciences in 2019 and named a highly cited researcher from 2014 to 2019. So once again, thank you, Professor Randall Snurr, for being here. You can feel free to start your presentation.
Thank you very much for the nice introduction, and thank you for the invitation. I see that this has been a very distinguished set of previous speakers, and I'm very happy to be here. And I see some friends online for the seminar. So let me share my screen. Are you seeing my screen?
Yes, Professor.
Yeah. Okay, great.
Nice.
Yeah, so I'm going to talk about how molecular modeling and machine learning can accelerate the discovery of new nanoporous materials. So I'll start with just an introduction to what my group does. Some of this was mentioned in the introduction, but we're interested in developing new materials and primarily adsorbents for separations and catalytic materials. And we're a modeling group, so we're trying to model these very complicated materials at the molecular level. And computers have gotten fast enough and algorithms are good enough that we can now do that in a way that's useful for engineering. So we try to take these tools and develop solutions for problems related to sustainability, energy, and national defense. And you can read here some of the things that we've worked on over the years, things like oxidation catalysis for green chemistry. Recently, we've started working on materials that can extract water out of the air for drinking. We work a lot on different separations, including CO2 capture. And there's some really interesting problems from the defense community related to either capturing or destroying toxic chemicals or chemical warfare agents. From a fundamental point of view, the group has expertise in adsorption thermodynamics, diffusion in porous materials, and catalysis. And the class of materials that I'm going to talk about are known as metal-organic frameworks, or Moths. And I think these are becoming pretty well known, but if you haven't seen them before, they're porous crystalline materials. So they're a little bit like zeolites, but they have a much more diverse chemistry. And they're synthesized in a very interesting way from metal nodes that are then connected by these organic linker molecules. Some of them have extremely high surface area, so they're very open, porous materials. And by choosing different nodes and linkers, you can make an enormous number of different structures. And you can think about tailoring these materials for different applications. And the two materials that I'm showing you here are from my collaborators, Joe Hupp and Omar Farha. They're in the chemistry department here at Northwestern, and we work very closely together on developing these materials. So there are literally thousands of moths that have been reported to date. There's a whole variety of different linkers, different geometries, but also different chemical functionalities. There's a variety of different metal nodes, and these can be connected in different topologies. So there's almost an unlimited number of potential materials. And so this has gotten people interested in different applications, like storing molecules in these little pores, using them to discriminate between different molecules for separations, directing catalytic reactions in particular directions, and so on. And what I'll talk about is how we can use molecular modeling and machine learning to accelerate finding top performing moths for a given application. So, like I said, there are thousands of moths out there, and I'll talk a little bit about developing a database of structures. But the thought here is, okay, if we have a large number of moths, in a brute force sort of way, we could just do molecular simulations on them and predict different properties. For example, trying to find materials that had high capacity for storing hydrogen. And if we're generating all of that data, it would make sense to think about reusing it and incorporating some sort of data science to make this process more efficient. So like I said, I'm going to mostly talk about developing tools, and I'll show applications of them as we go along. So I'll start by talking about developing a database of Moth structures. Then I'll talk about instead of just brute force running simulations on thousands of structures, can we use machine learning to accelerate the prediction of, say, absorption performance? Then I'll talk about adapting some tools from chem informatics, thinking about how to represent moths. And if there's time, I'll talk also a little bit about screening moths using density functional theory as a complement to classical simulations. So when people make a new moth, typically they will do X-ray diffraction, they'll figure out the crystal structure, and they deposit those structures in the Cambridge Structural Database, which is now over 1 million structures. And so you can go there and find moth structures, but they're not labeled moths. So we wanted to create a database of moths. So we had to think about basically a criterion. You look at a crystal structure in the CSD and you decide, okay, is it a moth? Does it have metals? Does it have carbon atoms? Are they connected in certain ways? You could imagine looking for certain motifs. Then you run into the next problem, that those structures typically still have solvent molecules in the pores. And if we're thinking about doing gas storage or separations in experiment, you would remove those solvent molecules. And so we want to remove those before we perform simulations on these structures. So we've developed ways of doing that in an automated way. Another problem is some of the structures that are deposited have different amounts of disorder, missing hydrogen atoms, extra hydrogen atoms, disordered carbon, different rotations of an aromatic ring, for example. And if you're only looking at one moth, you can put it in a visualizer and clean that up yourself. And what we did here was try to develop ways to automate that. So this was published back in 2014, a database of about 5,000 structures that we called computation ready. So the computation ready experimental Moth database, or core Moth database. And then in 2019, we published an update of this. It has about 14,000 structures. And yeah, these have been very widely used by both people doing simulations and people just looking for different Moth structures. I will point out here, if you want to use these, this cleaning procedure is not perfect. Because we had to automate it, it's not perfect. And so there may be an extra hydrogen atom somewhere. And so what I would recommend is, you can use this for screening, or what we do typically, and we use it for screening, but at the end then look at your top structures and make sure that they make sense. So with this database, we can do things like find moths that have exposed metal sites. In many moths, the metals in the nodes are completely saturated by linkers, but in some moths, the last coordination site is occupied by a solvent molecule. And when you activate the moth, you heat it, drive out the solvent, you can remove that solvent from the metal and expose that metal node. And those could be interesting for binding molecules or potentially as catalytic sites. So in this 2019 paper, we compared a couple different methods for detecting open metal sites. We were interested in duplicates. The same people will measure a crystal structure for the same moth or different people will do it multiple times. So there are a number of things that are reported in this paper. We can look at things then like the most common topologies, and if you're not into moths, that's probably not that interesting, but there are a wide variety of different topologies. We can look at the most common linkers, and yeah, this paper has been widely cited and I think been quite influential in the field. There are also other databases. So we have two databases of hypothetical moths, and then the people in Cambridge developed their own moth subset, which is now up to at least 69,000 moths. And the nice thing about that is they update this every quarter as new moths are deposited into the CSD. So we have plenty of moth structures. What do we do with them? Well, one thing my group has been interested in is hydrogen storage for fuel cell vehicles. And I won't go into the background. I'm going to kind of dive right in here. So this was a team effort led by my graduate student, Ben Busior. And we were thinking about this sort of pipeline of how you might discover moths for hydrogen storage. So we have this large number of moths. In this case, we were looking at hypothetical moths. And as I indicated earlier, one thing you could do would be perform Monte Carlo simulations on all of them. So we're doing grand canonical Monte Carlo, which allows us to predict adsorption isotherms, or the amount absorbed in these moths. So we could predict how much hydrogen is absorbed in each of these and find the top performing candidates. We could then go to our experimental friends with the top 50, and they could look through them and try to find ones that they might be able to synthesize and ultimately find something that could be used in applications. And so we have papers from 5-10 years ago where we did this. And for something like hydrogen, these simulations are doable on a large database. But for many problems, these simulations start to become a bottleneck. And so what we wanted to do in this work was develop a machine learning model that would basically replace the simulations. So there are a lot of different flavors of machine learning, and the type I'm talking about here is basically supervised learning. So instead of simulating 100,000 materials, what if we could simulate 1,000 of them and train a model then that could predict the hydrogen uptake, and then use that model on some large set of structures instead of simulating all of them in a brute force way. So this machine learning model could be evaluated in seconds or minutes versus hours or days per material for the simulations. So yeah, this sort of summarizes what I just said, that we would develop a model that takes some representation of each system and predicts the properties we're interested in. And one of the key things here is this so-called feature engineering. How do we describe each moth to feed into the machine learning model? And for adsorption, we and other people had started with kind of the obvious things like the surface area, the pore volume, pore sizes, and those methods work okay. But we had gotten to a point where they weren't working as well as we had hoped, or as well as we wanted. And so we started thinking about, how could we improve this feature engineering? How should we describe each moth for a machine learning model? And we started thinking, well, we're trying to reproduce the value that a molecular simulation would give us. And we thought, well, what goes into the simulation? So in grand canonical Monte Carlo, we were using a classical force field, and we imagine our structure in equilibrium with a bulk phase. And we don't simulate the bulk here. We could if we did Gibbs ensemble, but here we're just doing grand canonical. So we don't simulate the bulk phase, but we insert and delete molecules from the Moff to achieve equality of chemical potential with that bulk phase. And we also, translate and rotate molecules just like, in normal Monte Carlo. And, we're always evaluating this sort of Boltzmann weight. And we thought, well, in a very real sense, the input to this simulation is the following. Imagine taking the crystal structure and taking a hydrogen molecule and placing it at different locations in the material. And at each of those locations, you could calculate the energy that the hydrogen would feel. And so you would get this three-dimensional grid of energies. And in a very real sense, that is the input to the GCMC simulation. Now, of course, the Monte Carlo also accounts for hydrogen-hydrogen interactions as they move around. But this is, you can think of this conceptually as an input to the simulation. And so we thought, well, maybe we could use that as our set of features to describe each Moth. And my student, Ben, was taking a class on machine learning. We were kind of new to this, and he came back and he said, well, it's really hard to use a three-dimensional grid of numbers for machine learning. You can use a 2D grid, like in facial recognition. That's basically, a two-dimensional grid of pixels. But 3D was hard, and we were new to the field, so we thought, okay, we don't want to try that. So we thought, well, let's just make a one-dimensional histogram. We could take all of these energies from this three-dimensional grid and just bin them and plot the volume fraction at all these different energies. And that could be basically a fingerprint for our Moth. So we can do that. We can take a crystal structure, calculate the three-dimensional energy grid, convert it to a histogram, and the heights of these bars then are the features that will feed into a machine learning model. And so we can do that for a variety of different structures, and you can see each one has a different fingerprint, distinguishing one Moth from another. And so we want to take those values and predict the hydrogen uptake, and we'll train a model by calculating the hydrogen uptake from Monte Carlo, and then training, in our case, just a simple regression model to do this prediction. Let's look at one of these histograms a little more. So we have one bin here that represents all of the repulsive parts of the structure. So basically places where the hydrogen would overlap with the framework. And then we have these other regions that are the attractive parts where hydrogen would like to absorb. And we played around with things like the bin width, and the method is robust to reasonable changes in the bin width. So here's the model. It's just a simple equation. So Y is the hydrogen, the so-called deliverable capacity, which is the amount it's absorbed at 100 bar minus the amount absorbed at 2 bar. So 2 bar would be the delivery pressure. You can't get all of the hydrogen back out of the Moth. And this is at 77 Kelvin. So the coefficients here are what we regressed, and the X's would be the heights of the bars in the histogram for some given Moth that you're interested in. And one nice thing about doing linear regression is that these coefficients are interpretable. So for example, if we look at the coefficient here on the repulsive bin, you can see that it's negative, which is telling us those regions in the Moth are not contributing to the deliverable capacity. On the other hand, this next set of bars, these coefficients are positive. Those are regions of the Moth that contribute to having good deliverable capacity. And then if you go down here, you notice, well, these coefficients are also negative. Those are the gray dots. And you might wonder, well, these are really attractive regions. Why would those not be good for hydrogen storage? And the problem is that this is the deliverable capacity. So in these regions, the hydrogen is bound too strongly, and you can't get it back out of the material. So in some sense, I sometimes feel like I have to apologize for calling linear regression machine learning, but there's an advantage to a simple model if it works, in that the model itself is more interpretable. So let's see how it worked. So here's the training set. So we performed Monte Carlo simulations on 1,000 Moths, and we fit those coefficients. So the fitted capacities on the y-axis, the results from the Monte Carlo are on the x-axis. And you can see that the mean absolute error is 2.3 on a scale that goes up to about 50. So an error of about 5%. And we thought, well, that's good enough to distinguish top performing materials from the rest. So this is the training. Here are results then on about 1,000 Moths that were not used in the training. And you can see, again, we get a similar error. So then we took the model and ran it on this CSD Moth subset. So this was about 50,000 Moths from the Cambridge Structural Database. And instead of running 50,000 Monte Carlo simulations, we just used the machine learning model. And you can see we did a little more testing here, but again, the error is pretty similar. And so, yeah, like I just said, instead of running 50,000 Monte Carlo simulations, we run the machine learning model, maybe do some testing. We looked at the top 1,000 Moths then again, and we could then narrow down a list of candidates. And so we went to Omar Farha's group, our collaborator, showed them, I forget, maybe the top 50. And some of them they look at and say, well, that one's going to be hard to make, or, it doesn't look very stable or whatever. But this Moth they thought looked really interesting. So this was a known Moth from the group shown here, but it had never been tested for hydrogen storage under the conditions that we were looking at. So they went into the lab, made the Moth, performed typical characterization, looked at the surface area, the crystal, the X-ray diffraction, and measured the hydrogen uptake. And you can see here the comparison of what we predicted from simulation versus the experiments at 3 different temperatures. And at the higher temperatures, the Monte Carlo is spot on with the experiments, and at 77 Kelvin, we over-predict somewhat. And around the same time, Omar and some other collaborators had published a review article in which they collected the top performing Moths for hydrogen storage under the conditions shown on the slide. And you can see that this Moth that we identified is as good as any of those within the error bar. And we were able to identify this very quickly using this combination of molecular simulation and machine learning. So yeah, this simple lasso regression is accurate, at least for this system. It's interpretable, it's robust to small variations in some of the choices, and it's about 3 orders of magnitude faster than brute force Monte Carlo simulation. So it allowed us to rapidly screen a database of structures and identify a material that could then be tested in the lab. And this paper won the Senior Molten Medal from the Institute of Chemical Engineers in the UK 2 years ago. So this is one thing I liked about this award is it's for the paper. So all of the co-authors were winners of this, this award. Another thing to think about, we want to do machine learning, we want to use data science. This question of data management comes up. And in particular for moths, there's a real issue about naming these structures, which hinders the search for materials and also makes it difficult to categorize them and make some conclusions. So we set out to tackle this problem, and these are the collaborators on this work. And basically the thought was we need a Moth thesaurus. So if you go to Sigma Aldrich and want to buy this Moth, there are 3 different names for this in their catalog. They're all the same structure though. Even really well-known moths, ear moth 1 or moth is also known as moth 5. H-cust1 has all of these different names in the literature. On the flip side, there are 2 different structures in the literature that people have called moth 48. And you know, the convention here is people make new moths and they basically name them after their university or things like that. So moths from Northwestern, many of them are NU and then some number. H-cust1 is from the Hong Kong University of Science and Technology. But this makes it really difficult to search the literature. It makes it difficult to use certain tools from cheminformatics, and I think it's really slowing down the discovery of top performing materials for different applications. So we set about not to basically replace those common names. They're always going to be useful. But what we wanted was some sort of machine readable name. So our thought was that we would decompose moths into their building blocks. So there had been work doing the reverse in the literature. So people had started with a topology and placed the building blocks onto it to make crystal structures. For example, there's nice work from Rokas-Schmidt's group on this. We wanted to do the reverse, start with a crystal structure and break it down into the secondary building units, basically the linkers and nodes, and identify the topology. And our thought was, okay, we could build upon a lot of tools in the literature. So we have these different Moth databases. There are tools from cheminformatics to name linkers with these string representations like smiles or inchi. And there is a database of topologies from Mike O'Keefe and Omar Yagi. So I won't go into all the details. I'll just mostly say that this is much easier said than done. So for example, if we look at this Moth 505, it has this structure shown here. So copper paddle wheels and this linker. One immediate question is what to do with these carboxylates. So this is the organic linker that's actually used in the synthesis. So you might think, okay, I want to decompose it like this. But when people talk about these metal nodes, these clusters are known from inorganic chemistry. So this so-called copper paddle wheel. But the way this is always represented, the carboxylate's also shown here. So this carboxylate and these carboxylates, they're the same thing. So we have to decide, do we want to include it with the organic or do we want to include it with the metal node? That's one issue. Another issue is think about this linker. I could think of this linker as being a 4-connected node, right? It connects to 4 different metal nodes. Or I could think of it as 2 3-connected nodes that are connected like this. So this would be a node in a topological sense that's connected to 3 things. So a metal node, and this other organic piece. So there's 2 different ways that you could divvy this up. And we ended up needing to do this in multiple different ways to make this robust. And like I said, I won't go into the details. And there are lots of other special cases. So our method does not work for everything. For example, moths that have metal nodes that form these rods, we can't handle those at the moment. But we can handle a fair number of structures. And so here's what this looks like. We take the crystal structure, we break it up into the metal nodes and the organic linkers, and then there are tools from the literature that we use to identify the topology. And then we put this all together in what we call a Moth ID. So we have the inorganic piece, a SMILES string for the organic node or organic linker, this identifier, the topology, and then some other information here. We also have a second version of this we call Moth Key. It's a more compact version where we take the SMILES string and run it through a hash function. And so this, the latter might be something that you could search for in Google. So you could put this in a paper, and this would be a way to facilitate search. The first one might be more useful in, say, a database where you want to query, you want to find moths that have an alcohol group on the linker, for example, things like that. So we can do some things with this already, and we're finding it quite useful, but just a few examples. We can find duplicate moths. And that might sound like a simple thing, but when you start digging into it, it's a little harder than it sounds. Take two crystal structures and tell me, are they the same moth or not? If you break them up into this Moth ID, that facilitates that sort of identification. So for example, in the Cambridge Structural Database, when we did this, there are 92 different copies of copper BTC, 60 different copies of your Moth 1. And we could do things like take a couple of different databases and find how much overlap is there. And this was a common question we had. We had this database of hypothetical moths, or actually two databases of hypothetical moths. And people would often ask me, how many real moths or existing moths are in there? And this was a way to answer that question. We can identify moths that have the same building blocks, but different topologies. And that might be useful for understanding the effect of topology on, say, adsorption, because the building blocks are the same. They're not going to change the properties. And the Python code for doing all of this is publicly available. And for people who don't want to play with the Python code, there's also a website where you can take a CIF file, upload it, and it will give you back the Moth ID. And so, like I said, this is not meant to replace common names. And I view it as sort of a starting point, and the community really should come together and come up with some conventions for standardizing this sort of naming. But even this preliminary effort, I think, is starting to be really useful to my group in doing some analysis of large numbers of moth structures. This used a lot of open source software, and we were able to also contribute back to some of these open source efforts. And yeah, all of this is publicly available then. So in the last 5 or 10 minutes, I'll shift gears and talk about, this is less related to adsorption and thinking about other properties of moths. So yeah, what about other properties? Things that are best described not by classical Monte Carlo simulations or MD simulations, but by quantum mechanical methods. Things like optical properties, electronic properties, catalytic properties. And if you think these methods are even slower than molecular simulation, and that provides even more incentive for thinking about incorporating machine learning into the search for top performing materials. So as a starting point to do this, we thought, well, we need a database of DFT computed properties. So these exist for things like gas adsorption, but what about these DFT computed properties? And another thing that we thought would be interesting here is that moths may have their own needs in terms of features. Compared with isolated molecules or inorganic solids, where there's already quite a lot of work in the literature. So we published this last year. It's known as the quantum Moth database, or QMoth database. And it's a database not just of Moth structures, but also of their electronic structure properties, including geometries, energies, all of the things listed here. And I'm mainly going to talk here about the band gaps. And this work was led by Andrew Rosen, who was a graduate student in my group at the time. So first, we need a set of Moth structures. And we realized pretty quickly we couldn't use our core Moth database. So when we developed the core Moth database, we took a very inclusive approach. As I mentioned earlier, there are some errors in the automation of cleaning up these structures. And if you're doing Monte Carlo simulations for predicting hydrogen adsorption, an extra hydrogen atom on the framework basically doesn't make that much difference. Now, there may be some things that matter, but in many cases, the results are robust to those errors. But if you think about doing a DFT calculation, if you're off by one electron or one hydrogen atom, that could basically give you nonsense for the DFT results. So we decided that we would take a different approach. We would develop a new set of Moth structures, and that we basically would filter out any structure that had any kind of disorder. Omitted hydrogen atoms, fractional occupancies. Instead of trying to fix them, we just eliminated them. So we started with the CSD Moff set and Core Moth 2019 databases. We did remove the free solvent, the ones that are not bound to the metal nodes. And then we went through this cleaning procedure that I won't go through, but as I said, we got rid of anything that had disorder. We checked for things like, okay, if it doesn't have carbon atoms, it's not a Moff. We only kept things that had a pore limiting diameter greater than 2.4 angstroms. So we wanted some porosity. So yeah, a number of things that are shown here. And so we got this set of structures, about 15,000 structures. And now, instead of using classical Monte Carlo simulations, we did density functional theory. And we leveraged some work that Andrew had done earlier on developing high throughput periodic DFT calculation workflows that we had used earlier for catalysis. Because of the cost of doing DFT, we limited ourselves to Moths with less than 300 atoms per primitive cell. And we did full structure relaxations of these materials using this level of theory in VASP, and ended up with 15,000 calculations that finished. So this was about 170 years of computing time, and it's all publicly available, but let's focus on the band gaps. Well, okay, before I get to band gaps, here's the distribution of elements in this QMoth database. So all of the structures have carbons and hydrogens. These are the top appearing metals. And I will point out some types of metal nodes are likely underrepresented because of our choices about cleaning these. So zirconium Moths are quite popular right now. They're very robust. There are not that many zirconium Moths in this database because they often have disorder around the nodes. So one question we looked at, just a simple question, was people often calculate partial charges from DFT and then use those in classical simulations. How different are the charges that you get from a single point calculation on the experimental structure versus a DFT optimized structure? And you can see here, the charges are basically, they don't change between those small changes in the crystal structure. So that's sort of reassuring. And this had been shown by other people for smaller data sets. How about the band gaps? So here are the results. It's a violin plot of the band gap. This is all of the data. And we immediately noticed that there was this bimodal distribution. And when we looked into this in more detail, what we found was many of the structures down here that have the low band gaps, those are so-called open shell materials, in other words, materials that have unpaired electrons. And the closed shell moths, so the ones that don't have unpaired electrons, those tend to have higher band gaps. A reminder about what a band gap is, if from molecular systems, we're all familiar with the HOMO-LUMO gap. When you go to extended solids, instead of discrete orbitals, you have these bands. And so the difference, or the gap, between the filled band and the unoccupied band, the valence band and the conduction band, that's the band gap. And if this value is large, the material is an insulator. If it's smaller, it's a semiconductor. And for metals, the band gap is 0. And most moths are insulators. So we thought it would be interesting if we could identify moths that had very low band gaps. And so we trained a machine learning model to predict the band gaps using the data that we had generated here. And I'm running, I want to allow time for questions, so maybe I'll skip some of this. Again, we're doing machine learning, so we need some sort of features to describe each moth. And in our case now, we want to predict the band gap. And we tried a number of different features. So here was a simple one from the literature that basically just uses the stoichiometry. What fraction of the atoms in the structure are hydrogen? Helium is 0. We have some carbon, we have some oxygen. In this case, we had zinc. And then there's some statistical properties, the average atomic number, the mean polarizability, different things like that. So we use those as features. And this is a so-called learning plot. And you can see that the mean absolute error decreases as we increase the size of the training set. And the state of the art for predicting band gaps in inorganic solids is a mean absolute error of about 0.3 EV. And this was not doing as good, but it's kind of a simple set of features. We used a variety of other ones, and I will skip some of this. But basically, by using these crystal graphs as features and then using neural networks for the machine learning, we could get a mean absolute error of about 0.27 EV. And here's a parity plot, the band gap from the machine learning using the crystal graph convolutional neural network versus the DFT values, again, with the statistics that were in that table. And I'll skip this. So then with this model, we could try to identify moths that had low band gap. So we predicted the band gaps using machine learning on all 42,000 moths that we had structures for. And then we could look at the top performing, or in this case, top performing meant low band gap. So for example, the ones that had band gaps less than 1 EV. And it's known that the type of DFT we're doing tends to underpredict the band gap. So we ran higher level calculations on those and found some interesting structures. For example, a number of moths that had iron nodes. But if you're not interested in moths or band gaps, it's maybe not that exciting. So I'll just conclude here. I've showed you, some of what my group has been doing lately using molecular simulation, high throughput screening, some quantum chemical calculations to try to screen through large databases of nanoporous materials and find high performing materials. Throughout the talk, I hope I've shown you the value of open source software. One of the things I'm really excited about now is how much the community has embraced that. I think progress is just so much faster now because we're all sharing scripts and codes with each other instead of reinventing the wheel. And the last thing I'll just briefly mention, if you're thinking about separations, these materials ultimately have to perform in some sort of process. And I think there's a lot of room for chemical engineers to really contribute to this idea of combined material and process design. And my group has worked in that area a little bit. So I think I've mentioned collaborators and people involved in the work throughout the talk. So I will stop there and I'd be happy to answer questions.
So Professor Randall Snurr, thank you so much for the presentation. We are now open to questions. If you want to participate, please enable your microphone or write it down at the chat and we'll read it. Also, our YouTube viewers can write it down. Professor David has raised his hand. Please enable your microphone and ask the question yourself, please.
Yeah, hi Randy. That was a terrific talk. I really enjoyed every moment. It was very interesting and I learned a lot, I think. One question I had about the hydrogen storage part of it, you compared the moth that you identified as being optimal against a number of others that were known to be pretty good. I'm wondering if you applied your model to those moths to see if it would, if the model would have predicted those as well.
I don't remember if we did that or not, either with the machine learning or the GCMC.
Yeah, I think both would be interesting.
I mean, over the years, we've applied the GCMC to quite a few structures where we compared against experiment. So I think the GCMC is, it predicts these properties well. But yeah, testing the machine learning on these top performing ones would be an interesting thing to do. Yeah. Yeah, thank you.
Again, great talk.
Thank you.
Okay, we have another question from Professor Edward. Please enable your microphone and ask the question yourself, please.
Hi, Randy. Yeah, also really great talk. I also learned a lot. I'm curious about the histograms for the hydrogen part that you calculated. So those were calculated just like doing a potential map calculation, basically putting a grid, I guess.
Yeah, that's correct.
How sensitive are those to the choice of your force field? So, and I imagine with hydrogen, that's kind of a simple one. If you were to try to do CO2 or something like that, does that get to be a little bit more difficult?
We're working on it right now. So we've done alkanes where the grid is just the energy that a methyl group feels. And we can predict the adsorption up to about propane using just the grid of the methyl groups, and it works pretty well. When we go to longer chains, the performance started to deteriorate. And we have a paper almost ready to submit where we, instead of just looking at the energy, we also incorporated the gradient. Because the histogram throws away all of the spatial information. You have this lovely three-dimensional grid that tells you this site is beside this one. You put it in the histogram, you lose all of that. So we thought that incorporating the gradient would at least incorporate a little bit of spatial information. And with that, we can predict up to we've only tried it up to hexane, but we can even train it for linear hexane versus 2,2-dimethylbutane using just the energy that the methyl group feels. So we're basically trying to see how far we can push this.
And this is just van der Waals interactions. There are no electrostatics in this?
Right. So for CO2, what we're thinking is you could have one map with the van der Waals interactions, say for a carbon or the oxygen, and then you could have a second map for the electrostatics and try to use both.
Great. Thanks.
So Professor Ioannis has raised his hand. Please enable your microphone and ask the question. Thank you.
Thank you. Randy, great talk. I really enjoyed it. One question regarding the use of various properties based on which you train your machine learning model. Have you looked at diffusion coefficients and other transfer properties? Probably it's a little bit more difficult to use them in the training scheme. Can you comment on this?
We have not. We've thought about it a little bit, but no, that's something we have not tried yet. Yeah.
And can you comment also on the force field that you are using for the simulations that are used for the machine learning model?
Yes, yeah, I guess this is also partly related to Ed's question. For the guest molecules, we like to use the trap force field from Zeitman when that's available. For hydrogen, there's not a really great force field for the hydrogen-hydrogen interactions. The Leonard-Jones parameters for the framework we're just taking from UFF. And it's, I think it's surprising how well it actually works. It sort of says that maybe it's not that sensitive to some things. And then for something like CO2, we would put partial charges on the framework from DFT calculations. So they're pretty simple force fields.
Thank you.
Okay, any more questions? Oh, Professor Ami has raised his hand. Please enable your microphone and ask the question.
Hi, Randy. Very, very nice and interesting talk. Really enjoyed it. I have maybe a bit naive question regarding the way that you created these energy maps. And I wonder, how did you choose orientations? Did you choose a random orientation? Did you use like a Monte Carlo scheme to reorient your molecules? Because I think that could become more important if you're looking at, let's say, chain molecules or molecules that are too anisotropic, like CO2, for example.
So the hydrogen model that we're using only has one Leonard-Jones site.
Okay.
So there's no orientation for that molecule. And then, as I indicated, for something like ethane or propane, we're not placing the whole molecule at each site. We're just placing a bead, a methyl or a methylene group. So we've tried to avoid this question of the orientation. Yeah. Okay, thank you.
We have another question. Please, Tiago, enable your microphone and ask the question yourself, please.
Sure, thank you. Thank you, Professor Snurr, for the terrific talk. I have two quick questions, and it might be, again, naive questions, but the first one being that based on the video that you showed from the simulations of the moths, it seems to me that the moth structure is fixed. So I was wondering if somehow, because of the adsorption of hydrogen, for instance, could the structure of the moth change, or some sort of a phase transition could happen? So then the adsorption itself could change. So maybe I know that some people usually do grand canonical Monte Carlo and molecular simulations to relax the structure of the solid and then go back to the adsorption, a grand canonical Monte Carlo simulation, and do this process iteratively to relax the structure of the solid. So I guess my question overall is the structure of the solid, the relaxation of the structure of the solid of concern? And another question I had is that regarding the band gap calculations that you performed using quantum DFT. So you mentioned that you use the PBE functional, and you said that it usually underestimates the band gap energy, right? So then you follow up saying that you might need to use, for instance, GGA or some other functional. So could you please comment a little bit more on that? Because I know that the finding the correct functional for such systems are definitely complicated, and you can get different values for the band gap energies. So I was wondering if you could comment on that. Thank you.
Yeah, good questions. So the first question about Moth flexibility. There are some very famous Moths that are very flexible. And it can be driven by changes in temperature, but also by gas absorption. So Moths that have, kind of a narrow pore and then they open up when stuff goes in. We've basically avoided looking at those. So we assumed the structures were rigid in what I showed you. And we've sort of approached it as, okay, we're doing high throughput screening. You get the top results, and then you go back and look at them. And if you know, okay, related Moths are very flexible, then you can look at that in more detail or decide, oh, we don't want to consider that one. I think if you're thinking about like an adsorption column for separations, you probably don't want really flexible materials because they might not survive many repeated cycles. So many groups are looking at Moth flexibility, and there are all sorts of fascinating problems. We've mostly avoided it in my group, but it's an interesting area and can be very important. The second question, we have a follow-up paper where we actually looked at a number of different functionals and different levels of theory for predicting these band gaps. And what we found was, so it's known that PBE underpredicts the band gaps that pretty systematically. And yeah, I'm forgetting some of the details, but we found that whether the material had unpaired electrons or not made a big difference in how systematic the errors were. And we're sort of thinking along the lines of what you also hinted at, which is PBE is a relatively fast DFT method. And you could imagine trying to do some sort of like transfer learning where you could do a PBE calculation and maybe the machine learning predicts the band gap from a higher level of theory, that you could train that with, you know, some smaller number of higher level calculations. So I think there are a number of things you can do. And, you know, there are different functionals that people have tested for band gaps, and there's kind of a whole literature on that that we've started to tap into.
All right, thank you.
Any more questions from the audience? So our time is almost over.
I have a question.
Okay, sorry,
Maria.
Professor Fred, go ahead.
Sorry. I have a curiosity. You have shown us hydrogen adsorption and very nice correlation or calculation at high temperature, but at low temperature, at 77, it was not that good. And can you relate these not so good results by quantum effect for hydrogen?
So at the low temperatures, we are accounting for the quantum diffraction effects in a simple way. There are these Feynman-Hibbs corrections that you can do. So we are including those.
Okay.
They help, but it is quite systematic. It's not just this Moff. We've looked at other materials as well, and we almost always over-predict at the lowest temperature. And we spent quite a lot of time in my group thinking about why this is. And I'm not totally sure, but my best guess is that at the low temperature, the results are just more sensitive to the model, and the model is not perfect. But we are trying to account for these quantum diffraction effects. Yeah.
Thank you. Another question is, you have shown us a lot of very nice result about quantum mechanical DFT. We are using here in our group classical DFT. Do you think that classical DFT can speed up the calculation for screening?
I think so. Yeah. I mean, if it could replace the GCMC, yeah, classical DFT should be much faster, as you know. Yeah, it'd be an interesting direction maybe for more complicated systems.
Yeah. Okay. Thank you. The next question is about band gap. Do you think that we can control the band gap, by adsorption for appropriate molecule, in sense that you have now a physical control by absorbing some molecules or desorb some molecule? It kind of tuning the band gap.
It's a really interesting question, and I'm not sure. If the adsorbed molecules affect the structure, maybe the geometry, that could certainly affect the band gap. And there may be other ways to take advantage of guest molecules in the pores. Yes, I think it's a very interesting idea.
Thank you. Very nice talk.
Thank you.
Let's see, I don't see any more questions from the audience. So our time is almost over. I want to thank everyone for the discussion. And once again, thank you, Professor Randall Snurr, for the presentation.
Yeah, thank you for the invitation and the nice discussion.
So our seminars are being recorded and posted on YouTube, of course. After the invited lectures agreement, please check them out on our YouTube channel. So I think thank you. So this is our organization committee. We are responsible for inviting and communicating with the lecturers. We also handle social media, video editing, certificate writings, and hosting. So our next seminar is gonna be on June 9th at noon, and the speaker is gonna be Professor David. Let me see if Professor David is still in the audience. Maybe he can give a brief. Yeah, Professor David, do you wanna give
I'm
a
here.
brief? Okay. If you wanna give
yeah, we've been doing work. We're doing work trying to connect molecular properties to thermodynamic properties using cluster integrals. The virial equation of state is a prime example of that. So we'll talk about our efforts to do that and to try to develop models that are quantitatively accurate, and sort of progress in that direction.
Thank you so much, Professor David, for the brief description on the next seminar. So thank you all for being here today. See you all next Thursday.